Hey folks, welcome to session 4 of High Performance LLMs from First Principles. So again, thinking about how to achieve high performance in LLMs. And last week we looked at multiple chip perf, but honestly, I got a lot of questions after it about things that people were still thinking about, still working through. And I want to just do a little bit of work to make what's going on a little bit clearer for folks. So let's try to do that. So again, program, predict, profile. Hopefully we're going to get to all of those today in class. Please just raise your hand, speak up when you have questions. So we saw the system diagram, kind of how we're thinking about the overall system. We're still thinking about this kind of same problem, multiplying batch by E, tensor by 1 of E by E. And let's remember what the shardings were. So we had fully replicated, sharded by rows, sharded by columns. We are kind of still thinking, okay, we want the left and the right to be the same, so we don't want to change the sharding during the computation. But the weights can be sharded however we want. And then we get to kind of, again, data parallelism. And the reason data parallelism works, the reason we really like data parallelism, is it's embarrassingly parallelizable. The computation can just be done separately on each of the chips. So here, green and blue are chips, and it can be done separately. And another way of thinking of this is kind of equivalent, but finally a new picture for this week, is we can think about different computations for the different layers. And the way batch sharding by layers works is we've unrolled the computation here. So this is the first matrix multiply on the left, the second matrix multiply in the center, and the third matrix multiply on the right. And there are 3 different computations, and we just go through them left to right. And again, each of them is separable, so each chip just operates totally independently. There's no reason that the chips have to communicate. We don't even need the ICI for this to work. But when we get to fully sharded data parallelism, we're, again, storing only one layer at a time. And the observation that makes it work is that we can unshard the weights ahead of the data parallel matrix multiplication. But what I wanted to do is just add maybe a little bit of structure to that one, hopefully help this one make more sense by going through it step by step. So when the computation starts, we have the first layer's activations. We have all 3 weights, but we don't know activations layer I plus 1 or layer I plus 2. Those are things we compute. So the obvious algorithm, this would be a non-overlapped FSDP, is we unshard, we multiply, then we get the new one. We unshard, we multiply, and then we get the new one. The overlap algorithm, doing everything at once, instead looks like this. Okay, we just pretend the first layer started out unsharded, and then simultaneously, we do 2 separate things. So transition from step 0 to step 1, and so in step 1 back to step 0. We simultaneously compute the new activations, and we unshard the weights. And we'll do that again going here. So this runs in 2 steps. And then assuming that they can be done at the same time, and they take about the same amount of time, by doing the 2 operations at the same time, we just go twice as fast. So we'll definitely also code this and see the coding a little bit more. But before we go into any more detail, I just wanted to make sure folks were able to follow what was happening here, seeing the difference between a non-overlapped, so again, a non-overlapped version, where each thing happens one at a time, and then an overlapped version, where the 2 steps can happen at the same time because there's no data dependency between them. They're just 2 separate things that the chip is able to do at the same time. Any questions before we dive into the next one?
I have a question.
Absolutely.
If you unshard, like, once you run out of memory?
Yeah. Okay, that's a really good question. Let me address that one just by itself, and then we can talk about the next one. So the point is that there are maybe 100 layers that are going on in one computation. So I've drawn this pipeline only being 3 deep, but imagine there are 100. So now I have to unshard 1 or maybe 2 at a time, depending how I'm doing it. But I'm still getting 100x or 50x memory improvement. Does that answer your question, Juan?
Not exactly, because what do you mean by unshard in this case? Like
How many weights need to be yellow? right? So only one or maybe two.
Yes. I see it. Yeah, I understand.
Perfect. So 1 or 2 weights are yellow at a time, depending on how good you are at scheduling. So that is what makes it a little bit easier.
Mhm.
Cool. Do you have another question, Juan? That was a great question.
Yeah, that was it. Thank you.
Awesome. All right, so that's the key, like, magical advantage, is that only 1 or 2 layers need to be fully replicated, so yellow at a time. And as long as we are able to do the unsharding, so the transition from green and blue to yellow, faster than we can do the matrix math, we can fully hide that overlapping, that unsharding, and therefore we can run as fast as the matrix math. Cool.
And a quick question, Rafi. How do we control how many weights are we replicating?
Yeah, so normally the compiler will do that for us,
Okay.
but it's actually really easy to also specify it yourself in JAX. So I think that I'll try to work it into the material, seeing us do it ourselves, but also normally you don't bother. The compilers are very good at this.
Thank you.
Cool. Any more questions? Both great questions. Thank you.
Yeah, Rafi, sorry, this might be a little dense, but just to reiterate in my own words. So we are saying, since we are only unsharding the weights 1 layer at a time, we're able. I think the key point for me was we're able to do that faster than we do the matrix math.
That's the point. Yes.
So we're like, to make a metaphor, we're like laying down the railroad tracks as the train is coming, but we can do so faster than the movement of the train. Okay, cool.
Yes, that's the key for all of the math, is whether you can lay down the railroad tracks faster than the railroad, the train moves.
Yeah.
Because as long
Poor
as you're
metaphor.
able to, no, it's delightful. But as long as you can do that, the matrix math can happen fast, not be effective. But then once the unsharding operation starts to take too long, then the matrix math is impacted and starts to be an unpleasant trade-off. Yeah, great point. We can maybe show a better picture of that at some point, but that's exactly the right point. Cool. That's always going to be the mental model, just so you know. Like, it's always, we have all these things, they're racing. We want the matrix math to happen at full speed, and we want to not be blocked on that. So we need these comms to be fast enough to keep up with the matrix math. Cool. So that's FSDP. And we'll do a little bit of work on it today, just by programming and profiling. But I thought I would just do the equivalent for tensor parallelism next, okay? So tensor parallelism is actually like a little bit differently shaped. So in FSDP, we were overlapping between layers, but in tensor parallelism, we actually aren't able to overlap between layers because we don't know the activations in advance. So there's nothing, we can't do it. It just doesn't quite work. We could gather the weights, but we wouldn't have what we needed. So the way this works, and I showed this picture, but I wanted to just give a clearer image of it. So this is one way we could do it. We could first compute the matrices, and then we could add them. And that would be a non-overlapped tensor parallel, model parallel matrix multiply. But kind of the overlap strategy, we'll do it really in 5/4 the time we expect. So it's a little bit slower, but it's a lot faster than doing the two separately. So first, let's imagine the first step is we compute the partial here, and that's again a purely local operation for the chips. So none of the chips have to talk to do this. Then we will do two things at once. We will add the ones we've already computed and get the golden answers. So this is going to be called a reduced scatter, because we add both of the answers, but then each chip takes a different subset, and then we'll compute two. So we'll compute the second row. So I'm just going to do that 3, 4, and then the fifth step we finish the computation. So kind of like naively, this should take probably 4 steps, but what I'm showing here is this is kind of a very simple picture, and we can do it in 5 steps. Actually, as you make the pipeline shallower, so as you make this thing narrower vertically, you can actually make this as close an approximation as you want. So here, this is actually the same like analogy of building the tracks ahead of the train, but we're doing it one vertically as we go. Just wanted, it's not like the most important thing in the world to undertake. I just want to make sure that folks have a second to think about this. So again, the communications can be fully hidden, or almost fully hidden. Cool. And then the way to think about it is the amount of matrix math we have to do. Oh, it's approximately batch times E times E, so batch times E squared, divided by the number of shards, so batch times E squared over the number of chips participating. But the size of this reduced scatter is batch times E. So as long as E divided by the number of shards, so right, just dividing batch times E squared times number of shards by batch times E, we get E over number of shards. As long as E over number of shards is big enough, this is going to be something we're able to hide. And any questions about tensor parallelism, which is a little bit more complicated, but it has some advantages. Again, we don't even have to keep extra weights around. We can just overlap within the layer the communications with the matrix multiplications. There's so many good questions about FSDP. Is this confusing to folks? Happy to answer. I'd love to answer questions to help people get this one. Yeah, Zhang Fei.
Hey, Rafi. I'm not sure if I follow the upper set of the slides. I think the green and blue refers to a different shard, right?
Yeah, they're 2 different chips. And what we're saying here, this is a great question. So green and blue are different chips. And what I'm saying is green and blue have these 2 separate shards of the matrix, right?
Mm-hmm.
And the shards of the matrix have the property that when we multiply them, we get something of the right desired output, but it's not the full output. It's only a partial output. The green and blue's chips need to be outputs need to be added together to get the real output. So that's what we're doing at the bottom. Does that help, or do you have more questions?
Let's see.
So we've broken this up into 2 parts. One is each chip does the math that they have access to, and the second part is the chips work together to get the right global answer.
And then on the right, like after the badge, there are 2 green ones. Well, there are 2 green ones.
What I'm saying is that's the first pipeline. So I'm saying it produces 1 at time step 1, 2 at time step 2. But my observation is it has the same shape as the output, because the output is shaped batch by E,
Mm-hmm.
and the local output for multiplying the green's local matrix, the 2 local matrices is also shaped batch by E.
Okay, thank you, Rafi.
So yeah, so they're both able to compute the right things at the same right output, but not quite the right things. And then by adding them, they compute the right things.
Got it. Thank you.
Great. Any more questions? Glacier Bay.
Would this work if you reverse the sharding between the batch and the weights?
Yeah. So the case you're asking about, I think, is you're imagining flipping this one. Is that right, Sky?
Flipping both of them, or flipping one of them.
Okay. So flipping the left one, we get to FSDP. So the best algorithm will be FSDP. Typically, if you
Okay.
flip this one, there's the same trick, but you apply it on the left instead of the right. And that's called an all-gather collective matmul. I'm showing here a reduced scatter collective matmul. But this is a very similar trick.
Cool, thank you.
Great question. Anything else? Any more questions? I think this is like one of the hardest matrix multiplies. So just trying to make sure we get a chance to talk about it. It has a very special semantics, so that it can be overlapped within the layer. Cool. Well, feel free to ask more questions. Okay, all right, let's do it all together. So as always, programming live. This class might be extra dicey because I'm hoping to do some things on our cluster. So running on 256 chips. So I hope everyone's ready for some wild adventures in live programming. Let's just cool. So well, the first thing I want us to see is all gather. So we're just going to make array the same way we always do. So we'll just make jack.numpy.ones. Let's just have a size, matrix size. Okay, let's call it 16384, and we'll make this like this. So as we know from our experience, this is This is on a single chip at first. So we have to make a mesh. So mesh equals DAX dot sharding dot mesh. DAX dot devices. That's going to be actually fine here. And the access names. I think we can do our access. And then we can do a sharding equals jax.sharding.named sharding mesh, and we actually don't care how we shard this one. So we just want to show what does an all gather look like actually in this language. So it doesn't matter how we do it. We'll have a sharding jax.sharding dot partition spec, and this is our access, and then that's a sharded version, and then we equivalently can have an unsharded version. Sharding, if you will, and then we'll have an unsharded sharding. You decide how much of this names make sense to us. And that'll be none. And then we can jax.device put A onto the sharding. And we can do a jax.device put A onto the unsharded sharding. So this is what we are kind of like familiar with. And let me just run it to make sure I haven't messed anything up too bad. And what this should show us is this should just put A into the two places. Cool. So I guess I can put a breakpoint in. We can take a look just to make sure we remember how the things work. And then jax.debug.visualize array sharding. I think we probably all remember. Sharded A. Perfect. And then this one is sharded. I'm just going to go do uncharted, and then I'd love to field your question. Just reminding us what kind of we've worked on in the past.
Another question, quick ask. Can you make it a little bigger, please?
Yes, thank you. Let's make a little bit more space for you too. Can you see okay now?
Yes, thank you.
Oh, excuse me. And then I'm going to just visualize uncharted. All right, and that one's uncharted. Okay, so I think the thing that's kind of coming up is thinking about this overlapping. So the way I think we should probably think about the overlapping is, first of all, let's remember how we used to time things. So I have this timing util over here, which is simple time that it takes a function, args, and it just times it for us. So we can do that. And what we want is a function that does the unshards array, and it can take like input. And actually, it's going to be a funny function because it just returns the input. But how do we tell it, hey, I actually like this to be unsharded? And actually, the easiest way to do that, I think, is probably to do this all in JAX. So at partial, and we're going to do a JAX JIT, and then we have these helpful outshardings, and we'll say, well, I want my outshardings to be sharded. So now when we run unshard array, it's going to do the thing we want it to do. We've decorated, it's an identity function, except it knows its outputs are supposed to be unsharded. So we're going to unshard array A, unsharded A, at least we hope it's uncharted A, and then we'll just visualize that. And then hopefully that function will do the thing we want it to do. We could also do a device put here for multi-host code. This is a little bit more general, and we'll probably see that at the end of class. Cool. So unsharded A is sharded because we set sharded sharding instead of uncharted sharding. So let's. Perfect. All right, now we're cooking. Okay. Now we have timing util, so we should probably import timing util. And then timing util, that simple timer. Perfect. Unshard array, A, and those all look fine. Task equals unshard array. We can give it a name. Okay. And then let's run this. And then kind of the question we're always going to ask ourselves, whatever this number is this number fast? So the time it took is 52 milliseconds, so average time. And then let's figure out if it's fast. So achieved bandwidth is going to be, well, the size of A. So A dot size times 4, because A is going to be by default. Let's make this let's just control it. G type equals Jackson numpy dot b 16. So it's 2 bytes. So 2 bytes. So in GB per S. Okay, that's bytes. So let's go to gigabytes. Divided by average time milliseconds over 10 to the 3. Okay, so print achieved bandwidth. Okay, let's see how we're doing. Yeah, let's answer the question, especially because the numbers don't make sense on screen.
I think you need to exponent, not multiply.
Thank you. Is the question about exponential multiplication or something else? Feel free to just hop on.
Yeah, it was about that.
Thank you. Okay, so we're achieving 20 gigabytes per second. So is that good? Yeah, let's figure out. Let me see if I can find my handy dandy slides. Perfect. So what we're saying here, if we remember correctly, is that there are 3 axes, and they should be able to achieve 2.16 terabits per second in aggregate. So let's just do the math. The 2.1 terabits per second. First of all, let's go by 8. Let's do 2160. Let's divide by 8 to go to terabytes per second. So 270 terabytes per second. And actually, in this case, we only have 1 axis. So we should be able to get 90 gigabytes per second. But if you notice, we're getting 20 gigabytes per second. So I think 90 would be good. Not super happy to be seeing 20. Let's look at TensorBoard.
Hey, Rafi, what kind of TPU is this?
V48.
So they have 50 gigabyte per second.
Bidirectional though, right?
I don't know.
Bidirectional. Uh-oh. Can folks see my TensorBoard?
Yes.
Cool. So I actually have no idea what is going on here. So barrier cores mean that some of the chips are just not working. And then this is saying that we have a copy. So I'm actually a little bit confused by what this would be. I have to admit I did do this beforehand and all the numbers always made sense. So let's just take 1 second to look at the code.
Is this
And then-
multi-host?
Single host.
Oh man, I don't know then.
Yeah. Multi-host, this is more believable. Let's just make sure that we understand our inputs for a second. It's really most probably A. Oh, look at A is not, I never put A onto the sharded. Okay. So A is on a single device, and actually that's a really interesting lesson. But the algorithm it has to do is very different if A starts out sharded versus unsharded. So we'll just replace A with jax.device put A onto sharding here, and we will run it again. And then just let me make this bigger. I know folks need to be able to see. $83 gigabytes. Okay, there's a little bit of light cheating going on. And I'll tell everyone about that in 1 second. Let's just take a look at this log here. I think the barrier core was telling us that some chips weren't ready for. Okay, yeah. Well, okay, I guess I should just show people what this means. I think what's going on here is the different chips experience different barrier cores because at different times some of them are working and other are not working because the computation is asymmetrical. So anyway, fun fact. I've never seen that before. Pretty weird. Hopefully looks more normal now. Okay, and perfect. And we have an all gather. So we can see what the math is saying here. So it's saying, well, we started with something of 4096 by 16384. So that's one shard. And then we go to something of 16384 by 16384 by all gathering across all of the replicate groups. And the other thing is there's a little bit of waste here. So there is this copy. So if you think about this, like we're spending like 4.9 milliseconds doing the all gather, and we are spending 1 millisecond doing the copy. And the copy is really a transpose. It's preparing the data that's been all gathered to be like in the right format for subsequent use. It's a little bit unnatural because basically normally we have this like large jitted computation. So we wouldn't need to copy it to prepare it for like a formal output. But because here we're at the end of the graph, the XLI need to prepare it for output. And so that's again just like a slightly unnatural thing. I think when we go to more of these in the series, this will go away. But obviously we'll just have to keep an eye on that. Cool. So we got an all gather pretty close. Little cycle. Cool. Pretty close to the limit. 83.8 gigabytes. The one thing I want to say is we actually really did start with 1/4 of the data on each chip. So it's actually a little bit more like the performance is this times 3/4. So we aren't that close to the limit. So 62 gigabytes. We see we're losing a bunch of time for the copy. I mean, there's some overhead between the steps. But just to keep everyone, I think probably 63 gigabytes out of 90 is a more accurate estimate for how we're doing for this all gather. Cool. Any questions for an all gather?
Wait, sorry, I missed it. What's the 3/4?
We started with 1/4 of the data on each chip, Sky. So the all gather only had to collect the 3/4 of the data, of the global data that it was missing.
Got it. Thank you.
Cool. Cool. So I think the way to think about this, and maybe I should just put it into like a separate. I'm just going to make a copy. The way of thinking about this is okay. So we have this computation. We have some other computation which we can just quickly set up in class MATML, and then we have to race them, right? So I'm going to just switch to this one. Let's say, let's think about this as being our weight. Let's think about our batch is batch per chip, let's say, is equals 4096. Let's just make activations. And we can do that. We can be batch per chip times jack set device count by matrix size, whatever that can be embedding. We have weights. They're going to be matrix size by matrix size. Sounds good. And then our computation is now, we don't really care. Oh, we could do it like that, but we can just do it. We can make a weight sharding. And that we're saying is actually doesn't matter which one we do, but to, let's start with activation sharding. That one's actually really important. Activation sharding. And there we're going to shard over the first axis, but not the second one. And then in our example, we always shard it like this. So we'll just keep sharding like that. Activation sharding and weight sharding. We'll put the activations to be sharded. We will put the weights to be sharded. Perfect. Now our computation is just to do a matmul, right? So we actually, I don't think we need to tell them how we want it sharded on at the output. We'll just let JAX do that for us. And then we can do the matmul. And now we have to take activation, we're going to act weight. We need to do act at weight. We matmul, and then we can do activation W. Okay. And then I won't even do any calculations. And we're just going to go see a matmul. And there's actually a little interesting trick here. So the question of how is XLI and how is the compiler going to handle this computation? And we'll see how it does it. Cool. So what we should see is a separate all gather and then the matrix multiplication. But it'll be actually very hard for it XLI to find a solution that overlaps them because there's only one of these. So we can't overlap them between layers. So when we get into this JIT, we see that kind of exactly. So the fusion is the matrix multiplication that we're expecting, a per chip matrix multiplication. And this all gather is actually all gathering all of the weights together. But we are not doing the race yet. We are not overlapping the two. This one takes 4.9 milliseconds. This one takes 8 milliseconds. But there's no overlapping because there's only one matrix multiplication. So if we want to see overlapping, we have to give XLI a chance. And we have to have multiple of these in a series. So I'm going to go add a couple in a series. But before that, any questions? Do folks understand why with a single one, XLI might not be able to find a solution to overlap them? Basically, there's only one layer, so there's nothing to overlap into. Okay. Interesting. So TensorBoard is just crashing. So what we need to do is make weights, and we could just, doesn't really matter how we do it. W's equals for I in range layers. We'll set layers to be 4. W's equals DAC device put W for W in W's. And then weight for weight in weights. Act equals this. We will return act. and I will pass in W's here. So now hopefully we've done the same thing, except we have multiple weights. And when we run this one, now actually XProf has a chance. Actually, I had a chance to do the overlapping. However, we'll see if it actually does. I think we might need to give a little hint. Let's just take a look. Cool. And if I go to trace viewer, we're going to see now a bunch of matrix multiplied. So now remember our matrix, our JIT matmul now contains multiple matrix multiplies. However, each of them is their own little all gather and a fusion, all gather and a fusion. So we aren't getting any overlapping. So I did put the trick we needed into the slides. So hopefully I can do that. Perfect. So there's a little setting we have to put on this generation of hardware to get this effect. So I will just do this export. So this is basically telling the chip when it initializes to just be ready to do what we call dense, as opposed to doing sparse computations, as opposed to doing like DLRM or other embedding models. So it's just a setting on the chip. And now with the setting on the chip applied, so the previous time was 52 milliseconds, and we can just see how much faster this is. Okay, 39 milliseconds, so we got a nice speed up. And tensor board logged here. Cool. And if we jump over to trace viewer, now we should see the kind of what we expect, which is for the first layer, there's an all gather. But for subsequent layers, there's no all gather. We almost just see the fusion. And yeah, there's something happening in here. I'll gather structure that's telling the chip, hey, go get the next all gather. And then here we see, oh, hey, please start the next all gather. And then this one has the same. And then the last one, I guess, it doesn't do that because there's no need to do an all gather after fusion 3, after this matrix multiply, because there's no subsequent matrix multiply. Cool. So we've done kind of these 4 matrix multiplies in a row, and we've seen the all gathers all being hit. Any questions? Like, do people feel like they understand this? Is something I could cover in more detail, a little bit more? Vitaly.
Yeah, so why did we need like a flag to enable this? Like, shouldn't XLA by default do this?
Yeah, so there's a really technical reason. And the technical reason is if to get this ability to do this overlapping of this generation, the chip needs to be in a specific mode, and that mode has to be set at effectively as when it's being initialized, when its runtime is being initialized. I feel like Sky can keep me honest there, possibly, but but that's why this isn't on by default, is because we're losing other capabilities to get this capability.
I see.
Good question. Cool. Anything else? Any more questions? Seeing kind of this overlapping.
I actually didn't know about that special setting. Which TPU are you on? And do you need it V4? Do you need it on V5?
No.
Cool.
Megacore dense is the kind of weird setting you need. Cool. Anyway, we do document all of these things. It's pretty easy to find them, so not too tricky.
Yeah, Rafi, I have a question. Does this also work in the backwards pass?
Hey, sorry, my headphones cut out. Juan, could you come again?
Oh, does this work in the backwards pass as well?
I'm really sorry, Juan. I'm just not able to hear you.
Guys, can you hear me now?
Hey, folks. I think my mic is live. I don't think I can hear anyone. Can you just come in again once? Sorry about this.
Yeah, I was wondering, can you hear me now?
Okay, folks. Can anyone try speaking?
I'll try it again. Can you
Yeah.
hear me?
Well, I'm so sorry about that, everyone. Not sure what's going on here. What's up? We got one.
And I was just wondering if this works in the backwards pass as well.
Yeah. All the same tricks work in the backwards pass. They all have like an analog, so it's kind of like their weird sibling that works in the backwards pass, but they all do work in the backwards pass.
Thank you.
Dan.
Okay. I have a question. So often you don't do matrix multiplications in a row. You do them with like nonlinears, like ReLUs and so on. So do the ReLUs just stack onto the matrix multiplication since they're kind of independent of communication, and everything else happens the same way?
Exactly. They can effectively you can think of them as getting folded into the. I don't know what's going on here.
Yeah. Okay. Makes sense.
Sorry, I'm just getting. Sorry, there's something wrong. My mic is. Why don't we call things here, given that I'm having some technical problems? Yeah, that's definitely right, Ben. I'm sorry about this, folks. Let's just drop off. I'll turn off the recording. Really sorry about this, and hopefully I can stay out of these problems for next week. Thanks everyone for staying on.